We present CD-MPM, a set of continuum damage material point methods for efficiently simulating dynamic, brittle, and ductile fractures. Our first method, PFF-MPM, augments the material point method with a variational formulation for crack evolution by incorporating a non-local continuum damage-based phase field fracture model through a novel weak-form discretization. For our second approach, we present a new plasticity scheme that supports highly efficient analytic return mapping for a wide variety of plasticity models. Through this framework, we introduce an easy-to-implement non-associative CAM clay model capable of simulating a breadth of fracture phenomena. Although PFF-MPM and NACC plasticity work well together, in this work we focus on exploring them separately and denote which method was used for each demo. We begin with an overview of PFF-MPM basics. In material space, discontinuity is approximated with a continuous phase field. MPM uses particles to carry the phase field in world space, while the phase field evolution equation is discretized on a background scratchpad grid. PFF-MPM utilizes a staggered integration scheme with two system solves on the grid, one for momentum and one for phase. The blue and red arrows show key details in our data flow. The blue represents the dependence of the grid phase solve on particle deformation gradients, and the red shows the incorporation of the updated phases in the grid force update. We adopt a deviatoric dilational split neo-Hookean hyperelasticity to enable elastic degradation within PFF-MPM. Here we show the decomposition of the model into its tensile and compressive components, where only the tensile part is allowed to be degraded. With three realistic armadillos, we compare this hyperelasticity model with the popular fixed co-rotated and neo-Hookean models. Note, our scheme exhibits similar behavior. For our second approach to dynamic fracture, we propose an easy-to-implement non-associative CAM clay plasticity model with a novel fracture-friendly hardening scheme. Please refer to the paper and supplemental document for more detailed explanation. Compared with the cohesive CAM clay model used recently by Gomez et al., our NACC model better preserves volume due to our enforcement of a non-associative flow rule. Here, we show the effect of changing cohesion, beta, and hardening, alpha, for controlling the desired fracture appearance. Our general return mapping also works for the von Mises and Drucker-Prager yield surfaces. Here, we compare traditional MPM with CD-MPM for a high-velocity impact. Note that we combine PFF-MPM with NACC plasticity to demonstrate their successful union. The color reflects the phase field values, with red being 0 and blue being 1. The speed of crack propagation can be easily controlled with the crack mobility constant. Similarly, the resistance to damage can be controlled with the energy release rate. Now, we show some more 3D examples. We begin by showing some food destruction using NACC plasticity. Here, a sandwich cookie is dropped on the ground. Next, we smash a candy crab and visualize the NACC hardening parameter in material space at right. This multi-material watermelon is thrown at the ground at high speed, breaking into many pieces. Here we're smashing pumpkins. And this time, we visualize the hardening parameter in material space. Now for some less edible objects using PFF-MPM. Two octocats collide into a bowl with their material space phases visualized. During a high-speed bullet impact, traditional MPM breaks in a physically unrealistic way due to uncontrollable numerical fracture. Conversely, PFF-MPM produces a clear trajectory through the T-Rex. And here we visualize the phase field. A combination of von Mises plasticity and PFF-MPM phase field damage allows this car smash to produce ductile fractures with intricate shapes. Here, we tear apart a soft armadillo. And this time, we visualize the phase field. When twisting a jello bar with robotic arms, traditional MPM does not produce any fracture. PFF-MPM, on the other hand, produces highly detailed fracture. Finally, to celebrate the introduction of our CD-MPM methods, we'd like to break some bread with you.